This webcast discusses the friction force and dissipated energy. I'm going to work from the first set of slides that are listed in your OneNote notebook. Okay, so let's talk about friction force. Friction is a force that resists the motion when one object is trying to slide against another object. Friction always opposes that sliding motion, and as we've learned before, friction always acts in a direction that is parallel to the two surfaces that are touching, but it is always in the direction opposite to the direction that the object is either moving or trying to move. Friction depends on the types of materials that are in touch with one another. And it can be both a good thing and a bad thing. So there are many ways that friction is very useful to us. You know, for example, if you hang a picture or put a nail in a board, to construct something, it's friction that holds the nail in place. Friction allows the tires of your car to grip the road so that you can make a turn at high speed and you don't slide off the road. It helps us walk so that our feet don't slip out from under us. So these are all good uses for friction. But friction can also be harmful. In a car engine, for example, pistons rub against the cylinder that they're contained in, and it causes heat and wear and tear. And so friction can be a harmful thing that we have to manage. And the most common ways to reduce friction are to use some type of lubricating oil, like motor oil or WD-40, or a material that has a low friction. For example, Teflon is a very low friction type of material. So friction is caused at the microscopic level by the surface roughness. And this is a picture on this slide of two Velcro fastening strips. And you can see that on one side you have the little hooks there at the bottom. And on the other side, you have the threads or the things that the hooks are going to connect to. And so, the hooks grab onto those threads and it makes the Velcro pieces stick together. So not every material, of course, is exactly like Velcro, but they all have some similarity to that. So there are tiny bumps and valleys and things like that on all materials when you look close enough at the microscopic level, and that causes them to have this friction force when they try to slide against each other. So here is a blown up, greatly magnified photo of a surface of aluminum foil. Now, at the macro level, when we normally look at aluminum foil, it seems very smooth and polished, shiny, right? But if you magnify and the surface, you can see that it has these little hills and valleys, and every material has that kind of structure at its surface. And so the hills and valleys can grab onto each other, and that's the cause of friction. So we're going to talk through an observational experiment, and I actually want you to think back to the lab that we did for how net force affects acceleration. And I'm going to go to a PhET simulation that we used for that lab. So remember this simulation where we've got this orange man and he's going to push this crate. So first I'm going to ask him to push the crate with 50 newtons. Okay, so he's applying 50 newtons. I'm going to run the simulation. And see, nothing happens. The crate is not moving. And that's because he's applying 50 newtons of force, but the friction force that is opposing the ability of the crate to slide against this track is also 50 newtons. And since they are balancing each other, the crate does not move anywhere. And so, you know, that's this case here at the bottom of this slide, a small force being applied to a block on a table, but it's not enough force to make it to move. So we call this type of friction static friction. The word static, notice how similar it is to stationary. You know, when something is not moving, we say that it's stationary. So static friction is the type of friction that something is experiencing when it is not yet moving. Okay, so what if we increase the force that we're pushing with? Well, up to a certain amount, the friction force just keeps increasing. And we saw that in our lab in Unit 5, because here we were applying 50 newtons of force. Let's apply 100. It's still not moving, right? So I'm going to go up by ones now. 101, 102. Notice I've increased the applied force, and the friction force is increasing also. So static friction is not always the same amount. It can vary up to some maximum value. So the more that we push, the bigger the static friction. But it will reach a point where it can't increase anymore. Okay, so I'm going to go up faster. Here we are, 120, 121, 22. It's still not moving, right? The crate is not moving. 24, 25. Okay, here's going to be 126. And watch carefully. Right now, I've got 125 newtons, both of applied force and friction force. 126. Oh, look, when I apply 126 newtons, the crate starts moving, and look, the friction force jumped down. Now it's only 94 newtons. So what has happened is that we exceeded the maximum ability of the static friction to keep the object from sliding, and it started moving. Now we're in the realm of kinetic friction because it's moving, and so the friction force is no longer balancing the applied force. Okay, so static friction is able to increase until it reaches some maximum value, and when the block or the object begins to slide, then the applied force has exceeded the maximum static friction force. So static friction, it's a force that opposes sliding when there is not yet any motion. And it balances that pushing force, whatever it is, until the object begins to slide. Static friction can vary. It's not always the same amount of force. It's as much force as it needs to be to balance the pushing force. And but it has a limit. It has to be less than or equal to some maximum value. And that maximum value is calculated according to this formula. On the left, we have the force of friction, and you've been used to seeing F with an F subscript to represent the friction force, but now there's an additional subscript here. This S means that we're talking about friction in the static friction realm, and the static friction must be less than or equal to mu sub S. This symbol that looks like a U, it's a Greek letter called mu. Mu sub S means the coefficient of static friction, multiplied by the normal force, F sub n. Okay, so that is static friction. If the pushing force exceeds the maximum amount of that static friction, then the object's going to begin sliding. And once it starts sliding, it is still experiencing friction, but now the friction is called kinetic friction. Okay, you only ever have a single type of friction. It's static friction before the object starts to move, and then you're experiencing kinetic friction after the object starts to slide. So a lot of times we might want to calculate that maximum static friction. That would be mu sub S times the normal force, because we know that as long as we push with any force bigger than that amount, that the object will begin to move. Here's an example of that. Sam is pushing a wooden crate horizontally on a plywood floor, and they're telling us the coefficient of static friction, that's the mu sub s, is 0.5. And we want to know how much force would Sam have to apply to make the crate start sliding. Now in the vertical direction, the crate is not moving up or down. So we know that in this direction, the net force is 0. Therefore, the normal force is equal to the weight of the crate. Okay? We needed the normal force because the static friction depends on the normal force, right? It's the mu sub s multiplied by the normal force. So that's 0.5, that's the static coefficient, times the normal force, which is equal to the weight, or the mass times 9.8 for this crate. So as long as Sam pushes with something bigger than 490 newtons, the crate will start to slide. Okay, once something is moving, you're in the realm of kinetic friction. And so kinetic friction is the type of friction that opposes sliding while the object is moving. And here is the equation for kinetic friction. It looks very similar to the previous equation for static friction, right? But one thing that's different is that now we're using K subscripts to represent that we're in the kinetic realm. But notice here, there's an equal sign here. It doesn't say less than or equal to. Kinetic friction is always constant. As long as the object is moving, it doesn't matter how fast or anything like that. As long as the object is moving, kinetic friction is a constant value. This table provides examples of some coefficients of friction, both static and kinetic, for different types of contacting surfaces. And these coefficients, they have to be measured experimentally, or you have to look them up. So these are not something that you would be able to derive, or you wouldn't know them. You're not going to need to memorize them. These are just some examples. But take a look at this table. First of all, notice that there are no units of measure given on the coefficients of friction. And that's because these coefficients are a dimensionless quantity. The coefficients are actually, they represent the ratio of the friction force to the normal force. And so there are no units on these. And also notice that the coefficients of kinetic friction, that's in the column over here on the right, they are always somewhat less than the coefficients of static friction. Always. And usually the coefficients of friction, almost always, they are less than 1. So let's talk about that. So the coefficient of static friction is always larger than the coefficient of kinetic friction. It takes more pushing force to make the object start to move than it does to keep it in motion. And there are no units. The coefficient is a dimensionless quantity because the coefficient of friction is the ratio of the normal force to the friction force. So almost always the coefficients of friction are less than 1, but it is occasionally possible to have something greater than 1. Like in this table, at the first row says rubber on rubber, and there's something a little bit bigger than 1, 1.16 for static, 1.1 for kinetic. So think of things like a sticky note, for example. That has a coefficient of friction larger than 1. That, when you have a coefficient of friction that's larger than 1, it means it takes more force to make the object slide than it does to just pick it up. Okay? Okay. So let's talk through a couple of points that we should review. notice that frictional force is proportional to the normal force, not the weight of the object. The frictional force depends on the strength of the contact between the two objects, and that's really measured by the normal force, right? The normal force is the force that occurs because you've got two objects pressed together. And so the normal force is a measure of how hard they are pressed together. So be careful. There are situations where the normal force and gravitational force are the same amount, but always be sure that when you're calculating friction that you are using the normal force. Okay. And I want to also show one other simulation of friction to show what happens when two objects move against each other. So here we have two books. A chemistry book is sitting on top of a physics book. And this window here with all of the dots in it, this is blowing up and looking at the surfaces of the two book covers. And right now they're just sitting on top of each other. They have not been moving. And if you look, you can see that, do you see the little bit of vibration in all of these dots? That's real, right? Atoms are always in motion. They're always moving. But these are solid objects. And so the atoms, these circles represent individual atoms. They are rigidly bonded to each other, but it's like they're sitting in their chairs and jiggling. Okay, and so they're always moving a little bit. And notice over here on the right, there's a thermometer that gives us a sense of like how much heat there is, how much temperature on these surfaces. Right now it's pretty low. But now I'm going to grab the chemistry book and I'm just going to make it move. It's going to touch the physics book and I'm moving them together. Oh my goodness, look. As I rub them together, do you see how the temperature is getting larger and larger? And look, they're moving so much faster until they cool off. So when objects rub against each other, they heat both of the surfaces up. And the heating up that happens, it happens at a microscopic level. And so it causes some energy. We say that it causes the energy to dissipate, okay? Because the rubbing together gave them a higher temperature. Here's another example of that. Here we're looking, you can see the legs of a skier and the skis, and they've slid across the snow here. And over on the left, we've got a photograph that was taken with a thermal camera, and the colors here represent the temperature of what the camera is seeing. And so you can see that the snow mostly is very shades of blue because it's very cold. But where the skis have rubbed across the snow, you're seeing these green tracks because the snow and the skis heated up by that friction. And so friction causes energy to be dissipated or wasted. And that's because the excitement, the heating up of those atoms that causes them to dance faster in their seats, it's not a useful form of energy, right? We can't use it to do any useful work, but still the friction has used that energy. Okay, so we haven't lost the energy. We know where it went. It's just something that we haven't found a way to harness for useful work. So we call that dissipated energy. So dissipated energy we represent with E, an uppercase E with a subscript dis, and we're talking about unrecoverable, unusable, microscopic kinetic energy. And usually when we talk about dissipated energy, it has happened because of some type of friction.